So today we're going to finish up diodes. And of course, you guys know that we have a midterm exam on Thursday, and it's in this room. It's in this room. And remember, bring your ID. We'll check your ID. And when you came to the room, make sure you drop your backpack, everything on the side of the room. Just keep your computer or like pad for your exam. Okay. And then some of you still asking how the grades are counted. There are 5 problems. Okay. And the 5 problem sets. So 2 problem sets for chapter 2, 1 problem set for chapter 3, and 2 problem sets for chapter 4. And so you're gonna do all 5, and then we're gonna drop the lowest score. In each problem, there are a couple of questions. You need to answer all of them. You do get a second chance. And we do count the highest score for your 2 tries. Okay. If you think good enough, you don't have to do a second time. But if you didn't do well and you can do it again, hopefully you'll get a better score, and then you can we'll count the highest score. Any questions on the, yeah? What is it? Oh, yeah. When you finish the problem, you'll see your score right away. So if you're not happy, just do it again. It's within the time frame. You don't get extra time to do it. It's within that 1 hour and 15 minutes. You guys got to finish it. Yeah.
Online.
What is it?
It's online.
It's online, yeah. So yeah, try bring your laptop or iPad, whatever that you use to access the Canvas. It's on Canvas. Okay, so there are a couple of important concepts we're going to cover today. One of them is Zener diode, and another one is a small signal model, and the last one is rectifier. So let's go over Zener diode. Zener diode is a special kind of diode. It works in a reverse breakdown region. We talk about diode, the diode goes up, and in the reverse direction, it doesn't work until it breaks down. When you have a normal diode, breaks down, the diode is broken. You cannot reuse it anymore. That's a typical diode. But for a Zener diode, it's designed such that it can break down, it will still work. But it will give you a relatively constant voltage. It's like a voltage regulator. So it gives a certain voltage. Of course, that voltage is exactly a given number. It changes around going in it. But typically, you will get you can consider that as the constant voltage when it's breaking down. And it works, the Zener diode can work as a regular diode in the positive direction as well. So basically, if we complete the whole curve, it will just look like this. It just look like this. Yeah, so in the positive direction, it works as a normal diode. In the reverse direction, it works as like a Zener diode. And this equivalent circuit that we got is like this. It got a voltage. So when you add voltage onto any Zener diode, let me draw a few example circuits. Let's say you have a voltage. Oops, what happened? So let's say you have a circuit like this. So you know that it's 5 volts. The diode will give you 5 volts once in the breakdown region. You see the diode, it has like a little tilt, the special symbol for Zener diode. And whatever the resistance is there, let's say you get 1K. And then you can calculate the current is going to be 12 volts minus 5 volts divided by 1K. That gives you 7 milliamps. So that's your current in the circuit. Because the Zener diode gives you 5 volts, a constant voltage. As I mentioned earlier, if you look at the blue curve down below this X, it's not exactly constant. It actually changes when current increases. But again, for most of the cases, you can think Zener diode as a constant voltage drop on that. So now, if we change the circuit, like I'm going to give you 3 examples so you guys know what happens with the Zener diode. So this diode circuit, the difference between this circuit and the above circuit is that, let me do this. Better right here, close to me. The difference between this one is we use 5 volts like a voltage regulator. We use the Zener diode as a voltage regulator. So we connect a 10 kilo ohm resistance in parallel with the Zener diode. So now you see what happens because Zener diode dropped 5 volts. So you can still calculate I. Let's call it II, which means input voltage. It's going to be 12 minus 5 divided by 1K, give you 7 milliamps. And we can calculate IL. It's going to be 5 volts divided by 10K. That gives you 0.5 milliamps. So you can calculate Zener diode current. That's called IZ. It's going to be II minus IL. That gives you 6.5 milliamps. So your load draws some current. So initially the current in the Zener diode is 7 milliamps because everything flows in a circle. Now, because the load gets 0.5 milliamps, therefore the total current in the Zener diode is reduced by 0.5. You have only 6.5. So another circuit, it really gets interesting, is the same circuit, but I'm going to change this to 100 ohms, and this is still 1K, and this is still 12 volts, and then the diode is still 5 volts. So normally you would say, oh, the Zener diode can 5 volts drop, so I can calculate II, IL, II, and I Zener diode. So if you do what you did last time, you will say, okay, so II would equal to 12 minus 5 divided by 1K. That gives you 7 milliamps. And IL is going to be 5 volts divided by 100 ohms. That gives you how many milliamps? 50. 50 milliamps. So now you see what is IZ. If that gives you 50 milliamps, so it means this is 50 milliamps, but the source only supply what? 7 milliamps. Where did that 43 milliamp come from? And somebody may say, oh, you have a diode, can the current flow up there this way? Well, yeah, it can, but where would it supply it? So in this case, our calculation here is actually totally wrong because what happened is that there will be no current flowing in the Zener diode, which means you will not be able to sustain the 5 volts. So then how would you do this? Well, the idea to do this is that we're going to do it like this. We're going to do it a voltage divider. So we're going to do, let's call this VL. So VL is going to be 12 divided by 1K plus 0.1K times 0.1K. That gives you how much? 12 divided by 12.1. It's almost 12. So it's like very small. It's like 0.1 volt, less than 0.1 volt. So even though you have a Zener diode, but most of the voltage dropped on this resistance because Zener diode didn't get much current. So the little current goes this way, and then there's no current here. So the voltage over here is not 5 at all. It's like less than 0.1 volt over here. Because what happened? Because Zener diode, again, doesn't have current. So now you understand, for Zener diode to work, you have to flow certain amount of current in it. If you don't have current to flow in it, it will not stabilize the voltage. So that's the conclusion you can make. So Zener diode is relatively simple, not much to really talk about. Okay, so the next concept we're going to cover today is the diode small signal circuit. The small signal circuit just give you kind of the idea why this come up and how it works. We really don't use very much of diode small signal circuit. We use most of the small signal circuit in our future, like next 2 chapters. But here, the important thing is that if you look at the circuit on the left hand, you have a diode, you have VDD, and then you have R. So we would say the ID equal to VDD minus VD divided by R. That gives you the current for that circuit. One of the questions we want to ask is that what happens if that VDD changes a little bit? So sometimes what happens is you might have something like this. You might have a circuit, you have a voltage source, or you have something like this. You have like a DC, but then you have a little bit of this AC added on top of that DC. So it's like this. So if we have that, what would you get at the diode? So initially, that VD apparently is going to be like 0.7 volts for linear model. But if you have a little bit of change, so this is what happens. We have a little bit of change of voltage, and resistance the same, and voltage here is going to change, and current is going to change. So our goal is to find delta ID or so this one, what we're going to do is we're going to have to bring back the diode model. You remember the diode model we have ID equal to IS times e to the power VD over VT. So this is the voltage. So in this one, you will say, okay, so ID equal to IS e to the VD over VT. So that's this circuit. But for the circuit next to it, we can say it's going to be ID plus delta ID equal to IS times e to the power VD plus delta VD over VT. So this equation is for this one, right? So we just simply replace the voltage with like a little bit difference, and we plug in the same equation, the current will be different. And the difference we call it delta ID. So now we're going to extend this equation. If we know that this one VD, okay, so let me do this. So this one is gonna be IS times e to the power VD or VT 10 to the e to the power delta VD over VT. Okay, so what we are saying that if delta VD is small, this brings mathematics that you learned probably in your Math 150. If delta VD is small, e to the delta VD over VT can be written as 1 plus delta VD over VT. And then you got other high order terms. But if it's small, this Taylor series, I think is good enough to represent this value. So now we can plug in this one to that equation, and we'll get, so plugging this one to here. So we'll get IS e to the VD over VT 1 plus okay. So you probably noticed already. That already. What is this term about? This actually is ID, right? So this ID. So we can plug in this for ID and multiply by this one, and then ID multiplied by this one. So which means this is going to be ID times 1 plus delta VD over VT, and equal to ID plus ID times delta VD over VT. So you compare this side and the right hand and the left hand of the equation. So this ID will cancel. Then we will get delta ID equal to ID over VT times delta VD. So this is what we get. The final equation is the change of ID is proportional to delta VD and plus this one. So this one, if we flip this one, VT over ID, what do you get? It's a resistance, right? So we call that a small circuit equivalent resistance. So we will say the delta ID equal to delta VD over RD. And this RD equal to VT over ID. So this is very simple final equation is that for any small signal of diodes, you can use VT, which is 25 millivolts, divided by whatever current flowing in that circuit. Because this is a millivolts and this is milliamps. So usually this is in ohms, right? So let's say it's 25, this is 5, you got 5 ohms. If this is 25, this is 1, you got 25 ohms. So this is ohms. And delta VD over ohms, delta VD has to be a small number. It can't be like 5 volts. It has to be like 0.1, 0.2, or millivolts, just small change. And so millivolts divided by ohms, you got like milliamps. Sometimes it's less than a milliamp. So this is a small signal model that we derived for the equivalent circuit. In a graphical representation is what we are saying. If you look at this is the characteristics of a diode current in terms of voltage. If it's DC, you're working at exactly the same point. But if you have AC on top of DC, which means there's a small signal, or if the voltage changes a little bit, it's like that. So you get a little bit change in current and also voltage on the diode. So that is all because the change of the input voltage. And that whole thing can be solved by using a small signal equivalent circuit. So where did we get this circuit? Well, remember from the previous discussion we had ID equal to, so IS, let me write this back. So this is the actual the DC. But for AC, we had delta ID equal to delta VD over delta VD over RD. And this equation here gives you the actual current of the diode circuit in small signal. So from here you can see. So this is delta VD over delta VD over RD, right? So the question is that how would you draw the circuit? Well, if we draw the circuit, so this will be delta VD. It turned out that if you want to really calculate the whole thing, like what happens if that change to be reflected back into the delta VDD? So if delta VDD changes, what happens? Therefore, you have to add this R back to get the circuit. So this is where we add this R back to get. So in this circuit, you will have delta ID equal to delta VDD over R plus RD. Or this also can be said to be delta VD over RD as well. This again, we're not going to spend too much time on it because again, really not very much useful for small signal model for diodes. So you guys can probably just take it at this point, and then we can like move on to talk about something else. So there a couple examples in the book. asking you to calculate the current and even design the resistance such that you got so much voltage on the diode for a given voltage change. So this circuit, this is the original circuit. You have V plus supply power to R and a diode. So very simple circuit. If we take it as an ideal diode, and it would be just V plus over R, you get the current. If it's a piecewise linear model, you will have V plus minus 0.7 divided by R, you get also the current. But if it's a real diode, it's a splice model, and then we'll have to calculate how much current in that diode based on the voltage drop on the diode using the actual circuit. Now, what happens if V plus change a little bit? So what would you get for VD? So that is the question that is asked. So let me see, I'll bring the actual. Yeah. So 4.5. One second, I'll bring the original problem up so that I can write it down. Yeah. So the ask is R is 10K. And ask you to, the V plus is 10 volts. And which is superimposed on 60 hertz sinusoid 1 volt peak. So this is where it gets interesting, is that the voltage V plus is 10 volt plus like one how many 60 hertz 1 volt peak amplitude. So it's like plus minus 2 volts sinusoidal omega t. And I want to ask you, so you're going to ask you how much the calculate both the DC voltage of the diode and the amplitude of the sine wave for input appealing across it. So assume the diode has a 0.1 volt drop at 1 milliamp. So 0.7 volts at 1 milliamp. So that's the property of the diode. So if it conducts 0.7 1 milliamp, it's going to drop 0.7 volts. But we don't know how much the current is going to be. So the voltage drop may not be exactly 0.7. So we'll have to calculate. Okay. So what we're going to do is we start assume assume VD 0.7. So we can calculate ID equal to, that's the middle circuit. The middle one is the DC circuit. So it's going to be 10 volts minus 0.7 divided by R is 10K. So you got 0.93 milliamps. So at this point, what we are saying that, well, if we assume it's 0.7 volts, we get the current of 0.9.3. So this is close enough, right? But if you are not happy saying, well, it's not 0.93, so I have to go back to use the equation like what we said before. The equation is ID equal to IS to the e to the power of VD over VT. You can do that, but you're probably going to be fine that voltage drop is 0.697 or something like that, and the current is going to be close to 0.935, something like that. Okay, so that's that. So basically, what we're saying that the 0.93 is close enough. But if that ID becomes like 2, 3, or 5 milliamps, you have to be very careful because that is too much difference from 1 milliamps. The voltage drop start to change. So now we're going to say how much. Remember from the last slide, our ID equal to dirt VD over ID. And dirt VD is 2 volt peak. divided by ID is 0.93, which is close to 1 milliamps. Oops, sorry, this terribly is VT over ID, so it's 0.93 divided by us is 0.25 millivolt divided by 0.93 milliamps. That gives you about 26 ohms. So that's the equivalent circuit of a small signal model. You get roughly 26 ohms. And now we can calculate, we can draw this circuit like this. This is a circuit that we developed from previous slide. So that Vs is coming in. That Vs is the peak, the AC current, and RD is the equivalent resistance, R is the original 10K. So you got VD equal to RD over R plus RD times Vs, which means it's going to be 26 over 10K plus 26 times Vs is 2 volt peak, right? So we get 2.68 millivolts. The reason we want to look at this example is that if you look at the change at the diode, at the source, it has 2 volts peak-to-peak change. But at the diode, you only get 2.68 milliohms change. It's not a lot of change on the diode side. So this is quite an interesting phenomenon that when you apply voltage on at the source, and the change on the DC side is not very much. Okay, so I think I'm gonna. So this is a very similar example. I'm gonna skip it. And then going back to do a Zener diode example. Let me see what that says. Yeah. So this Zener diode, let me write down the numbers, is VZ 6.8 volts. IZ is 5 milliamps. RZ is 20 ohms, and IZK is 0.2. So I want to look at this together because the important thing that you see, the Zener diode was marked as 6.8 volts. That voltage, you have to conduct a current of 5 milliamps in it. So if the current is less than 5 milliamps, that 0.5 volts will be less. If it's more than 5 milliamps, the voltage is going to increase. But around 5 milliamps, you will get 6.8 volts. Right? So if you have 0.5K at the top, you can start to calculate the current. So you can calculate, let's go IL, IZ. So IL will be 6.8 divided by RL. Was RL given? No, RL was not given. But we can calculate I. That's going to be 10 volts minus 6.8 divided by 0.5K. So it's 6.4. 6.4 milliamps. If you consider the change, what it says that if the input voltage 10 volts has a change of plus minus 1 volt, and we want to look at what will be the load current. Now, if that changes, what we're doing is we replace the Zener diode with the equivalent circuit. And the equivalent circuit with Zener diode look like a voltage drop and a resistance. Okay, so that we didn't discuss in the previous slide, but here we give you the model of the of the diode. So instead of this one, we can do actually time minus 6.8 divided by 0.5K plus RZ. RZ is given at 20 ohms. So that only changes like 3.5. It changes a very small amount. So by this point, we want to understand this RL has to be big enough so that it doesn't connect more than, let's say, a few milliamps. Why? Because if RL is too small, if current IL is too big, then your IZ will drop. So IZ is equal to I minus IL. And this has to be larger than just typically around a few milliamps. It has to be a few milliamps. Yeah. And yeah, so the multiple questions, and you guys can go through the example later. So by changing the voltage source, we replace that, and we can eventually find out how much the load resistance, even for the small signal, when it changes plus 1 minus 1 volt, and see what happens on that. Okay. So for the remaining time, we're going to go over to rectifier. So one of the biggest function of diodes is to rectify AC. Rectification is useful that we almost do it every day. From the signal perspective, you rectify to become a DC for control purpose. But for power supplies, when we get power from the wall, we have 60 hertz AC, but almost all electronics use DC. How do you get DC? Rectified. So whether your phone charger, laptop charger, or whether you have a television or all that stuff at home, in industry, we use rectifier, we use diodes to rectify AC into a DC. A typical rectifier circuit consists of a couple of stages. So you will have a transformer on the AC side, and you transform that AC from a high voltage to a lower voltage, and then you get a smaller AC, and you rectify. And then after rectify, you do a filtering. So you get rid of the ripple, and from after the filtering, you get a certain DC, but it's not a constant DC because that in the change if the AC input changes. But for a lot of applications, you want a stable, like fixed voltage. So what do? You do a voltage regulator. And that voltage regulator has both linear and non-linear. So for electronics, for small signal, we all regulator. But for high power, more than like a few tens of milliamps, we would use a switching power supply. So it's a voltage regulator, but it's not linear. The purpose to increase efficiency. So you guys are going to learn this in 584 for the switching power supply. For the voltage linear regulator, you're going to learn this in 430 a little bit. Okay, so this thing work in a rectifier using diodes. All right. So this is the simplest diode that you can get. Is by connecting an AC through a diode to a resistance. And we had this many times illustrate how it works. If it's a real diode, you would have a little bit of voltage drop. So therefore, the output, the blue line, is a little bit less than the black line. If the black line is less than 0.7, your diode is off, so it won't conduct. Once it goes over 0.7 volts, you start to have current going through the load resistance. But it's minus 0.7. So like it's the difference from peak to peak, from the peak input to the peak output is 0.7. So when the voltage is negative, you see when the voltage is negative, your diode So therefore, you have this half wave. So we call this a half wave rectifier. So it's like you only get half of the input. The other half is abandoned. It doesn't pass through. So efficiency like this is pretty bad because you're wasting half of the input. Only half positive goes through, another half is wasted. So this is the simplest that you can do. If we want to do a better, see, we want to get a better output, we would do one of two options. So one option is we connect a middle point in a transformer. So the transformer has a primary coming in, and on the secondary you have one winding, but it has a sending tap. So the sending tap divides the voltage, output voltage into two portions, the top and the bottom. And what we are doing is we connect diodes on the top and the bottom. We use the center as a ground. So in this case, when voltage is positive, current flow this way. When voltage is negative, it flows this way. So therefore, at the output, what you get is when it's positive, you get this curve, which that's black minus 0.7, you get blue curve. When it's negative, you get the bottom half working. So also you get the black curve, flip it over, minus 0.7, you got this half. So you got this one. The output is full wave rectifier. But still, even though we get the output get full wave, which is better in terms of waveform because now you have pretty much waveform over one cycle. But still, when the top winding is working, the bottom is not working because it doesn't supply power. When the bottom winding working, the top is not working because the top doesn't supply power, right? So this is not ideal, even though it works, it gives you a full wave rectifier, but that's not the best. The best that we want to do is not to through the sending tap, but to go through a bridge rectifier. So the bridge rectifier, when voltage is positive, the current flows through two diodes through the resistance. So you have positive here, negative here. When voltage is negative, though, it will flow and you can see when the voltage is negative, you still flow from the right hand to the left hand on the resistance. So therefore, the resistance is positive regardless the polarity of the input. So when input is positive, you go through D1 and D3, D2. When input is negative, you go through D3 and D4. So we have an equivalent circuit on this side. Now, of course, you have two diodes, it's going to drop twice voltage drop, like 0.7 plus 0.7. So the output, instead of minus 1, like 0.7, now the difference is 1.4. So you have positive, you got here, and the negative, you go through, like, let me write down. So if when it's positive, you go through D1, D2, or negative, you go through D3 and D4. But the voltage drop is 2 times VD. So therefore, your output VO peak is V in minus 2 times VD, the peak. And if we draw the curve, it's going like this. So this is a very useful rectifier. Yes, go ahead.
It seems like the full wave rectifier would be better. You don't lose as much power, but is this better because it's less strain on the diodes?
Yeah, it's better because you get a full wave and you don't waste any of the winding voltage. Because in the previous slide, you saw only half of them is working at any given time. So ideally, the size of this one will be half the size of the previous one. Okay. On transformer, yeah. But the downside is that you do have two diode voltage drops at the output. So it's a trade-off. It's also costs a little bit, well, it not necessarily costs more because even though you use 4 diodes, but your transformer is less expensive. The previous diode used 2 diodes, but your transformer is bigger. So now the next question is that for this waveform, it's okay. We have like positive, but it's not exactly DC. Yeah, you got this. So in order to make this useful, we have to do filtering. Otherwise, this will destroy your electronics. And I have an experience. That was about 25 years ago. I had my first cell phone, and my charger was broken. So I went online and bought one. That it charged my phone like for a couple of times. My phone is not charging anymore. I said, what's going on? When I went to the lab, I found, well, the output waveform is crazy. It doesn't rectify at all. I mean, it doesn't rectify, but it doesn't do the filtering at all. It gives like this crazy waveform. Like, I mean, not exactly this, but it's more like a lot of ripple in it. So it didn't work. So how do you do filtering? Well, ideally, this has 60. Means DC is kept and AC is gone. So we need really to have a low pass filter. And for low pass filter, you get like a C. Well, one of the best way is simply just connect to a capacitor. So this is one example. You have a capacitor, and then you have AC coming in. So when you have AC coming in, you see what happens. When AC starts to increase, it's going to charge the capacitor, and all the way to the peak, all the way to the peak. Minus, I would say, minus the voltage drop on the diode initially, but eventually the current is going to reduce, and the voltage of C is going to increase until it reaches the two sides. It's going to reach the same, okay, almost the same. It might still have a little bit difference because the diode is going to have some voltage drop. You see, the idea, the diode have a voltage drop, remember, we said 0.7 at 1 milliamps, is that one diode does not have any current, the diode is not going to have a voltage drop. So eventually, if you put it long enough, the output voltage VO is going to be same as VI peak. Now, in this circuit, we don't have any load. We don't have any load, right? So the voltage is going to stay. So when the AC voltage drops, what happens? Are you going to have current anymore? So when AC voltage drops, your VO is larger than VI, which means your diode is reverse biased. So current is not going to flow back. The voltage is going to stay. So therefore, the current goes up, it stays. It doesn't come down. It doesn't come down. So this is interesting because, well, if we got a capacitor, it seems that it's going to work. It's going to give us a DC. But the problem is that as soon as you connect a load resistance, what happens? So let's say your voltage. So initially, it's going to increase. But at this point, your voltage start to decrease. But your voltage at the peak is going to, this VO, so then your VO is less than your VI is less than VO. So therefore, your ID is 0. So current doesn't go back. So there's no current going back. If you have no current going back, but you have resistance, that C has a voltage, you still have current going to that resistance. So you have current going through that resistance. We call it I. So I equal to VO over R. Oh, now I want to ask you a question. So if you have a voltage, you have resistance, and the current goes through the resistance, what happens to the voltage itself? Would it stay? Yeah.
It'll discharge until.
It will reduce because every time every moment you have current flow through R, you consume some energy, so voltage drop a little bit, and depending on how big the resistance is that, you could be dropping like all the way to 0 before it charge again. But if the capacitor is big enough, you might have something you can drop here, or you can drop like right over here, and it start to charge again. So the C is bigger, C1, C2, C3. So if C is not big enough, it will drop down to 0 and it will wait for the next cycle to start. But if C is big enough, your voltage will drop, but some point it will hit here and it will go up again. And how much would that drop? Well, we can solve for the circuit is C. We can do this. So voltage, we can write an equation for this one. So we can write an equation for this circuit over here. So it's just equivalent circuit. And this we all start with this R, and this is current. So current equal to V over R. Then also I equal to also C dVO over dt. So basically we have this equation here. So for this equation, you know, it's a first order, you can solve for it. So it's going to drop a little bit. And basically we can do, so instead of solving that equation, we can do some sort of estimation. The reason is that from here to here, if we want to maintain the voltage all the way like close to this point, so from here to here, how much time do we have? It's like TS. It's like the period. Just little, up to here is TS. Up to here is a little bit less than TS. So we do an approximation. We say, okay, that's TS. So what we're dropping is, so from here to here, we say it's TS. But when you drop up to this point, it's just slightly less than TS. So this T is less than TS, but that's okay. If we assume that's TS, and the other thing that we're going to assume the voltage is going to be, say, linearly drop. So then you will say, okay, so C delta V over delta T equal to this I, which is V over R. So we said when we had delta V equal to V O over R, oops, V O over R times delta T over C, which is V O over RC times delta T. So if we do this approximation, we can calculate how much voltage is dropped from here to here. So what we're saying is the delta V. So from peak to all the way how much is dropped, we can get that. But of course, this is very much approximated. It's not accurate, right? But at least it gives you the idea. If the C is big enough, the delta, see, what it gives you here is that if increase C, delta V is going to reduce. When C approaches infinity, that delta V is 0. And so you don't have any drop at all. So that's what the idea. If C is small, then the voltage drop is bigger. Because the delta T is the period that's given. Okay, so here is exactly what I just explained. How to calculate the voltage drop. Now, if you have a full wave and then you have a C, so apparently now the circuit, remember the circuit is like this. Circuit is like, for full wave rectifier, we have, let's do it this way. It's actually easier. So in this circuit, it's the same circuit as we drew earlier. So when you have positive current, when you have positive voltage, it goes like this. When you have a negative voltage, so you always get positive at the output, and then output can be drawn like it's like a full wave, minus 1.4 volt. And then if we have you have a capacitor, which is every time it's going to drop. So every time the voltage drop a little bit, but then it will go up again in half wave. So in this case, if we want to calculate the voltage drop, you already probably know easily that this voltage is going to be VOORC times delta T. Times this half TS. So it's going to be TS over 2. Oops, sorry. Times TS. Is it times TS? Times TS. Yeah, times TS. So in this case, the delta T we said is TS. You guys remember this one? So here we're going to have TS over 2. So apparently the requirement for C to reach the same voltage drop is half. It's easy to understand because you have half. Now we have full wave rectifier. The previous half wave rectifier. So you can do the calculation on the circuit over here. Basically, from here to here is TS over 2, right? So basically, you have equivalent circuit like this. And this is Vs minus 1.4 volt. And this C, this R. And then, so VO apparently is the peak of VO is equal to Vs peak minus 1.4 volt, but VO average average is going to be VO peak minus plus like VO the lowest value, which is this point over here. So this is peak, this is VL. So plus VL divided by 2. That will give you the output average, because the voltage rise a little bit and drop a little bit, rise a little bit, drop a little bit. So you really have some ripple at the output. And sometimes you can take the average between the peak and the bottom and the lower value. So divide by 2, that gives you. And then the third way, or you can write this down as like so you can write all this down as VOP minus delta V over 2. So it's the peak, and divide by half of the ripple is the average. Okay. Okay, so we have a few more diode circuits, and we just want to cover them. Like in addition to the rectifier, like today we'll talk about all applications. Okay, so Zener diode is the application of a diode, and rectifier is the application of a diode. And now we're going to talk about a few other special applications. So what is called a super diode? A super diode is simply by connecting a diode as the output of op amp. And when you have input coming in, and you have a certain output, by the name of super diode, you probably can already understand why it's called super diode. It does not have a voltage drop. So our diode, even though sometimes we use an ideal diode model, but that's not real, because in real life, you always have voltage drop. So how can you do rectification not losing any voltage on the diode? So now you have a super diode. How does it work? Well, it's very simple. You guys learned op amps already. So by op amps, you guys know that, right? V plus, V minus. Remember this, right? And op amps, op amps, almost all the time we can think them as an ideal amplifier because their amplification is so big, minimum like 5,000, 8,000. So it's really very big. So therefore, op amps, almost all the time, this is right. And also, I plus and I minus is 0, right? So this is also another characteristic of op amp that you learned before. So in this case, we connect Vi, V plus. Okay, so what would you get at VO? You look at the circuit, VO is connected to where? To the minus sign, right? And V minus sign is same as V in. So you will say, okay, so VO will be simply V I. This seems to be initial observation, seems to be okay. We got input coming at the positive terminal, and I got inverting terminal, same as the non-inverting terminal, and my output is connected to the to the inverting terminal. So this must be the case. Well, you have to be careful. If Vi is larger than 0, and you say VO is Vi. Now, the reason we want to do is we want to find the current. So you say, what is I/O? I/O is going to be VO over R. And what is ID then? So you have I/O going down through the resistor. So how much is ID? Can you do a node analysis on that VO? It's I/O. Yeah, because there's no current coming from the inverting terminal, non-inverting terminal, inverting terminal, right? So ID is I/O. So everything seems to be perfect, no problem. But what happens if Vi is, let's call it less than 0? What happens? You can still say VO is equal to Vi. Maybe. But if that is the case, how much is I/O then? So now it's still Vi over R, but it goes up because VO is negative. So VO is less than 0. Therefore, I/O is less than 0. I/O less than 0 means I/O goes up in the resistor. Now, can you tell me, is it possible? Why not possible? Because no current can go through the diode. So you have current flowing up from ground to R. It cannot go to the inverting terminal because it takes 0 current. It cannot go up through ID. So therefore, it's impossible. So what we are saying is, no, it's not possible. So not possible means VO cannot be, VO cannot be less than 0. VO has to be large or equal to 0. Otherwise, you would have current flowing. That's not possible. So if it's not possible, VO has to be larger than 0, which means, but in this case, it's also not possible to be positive because your input is negative. So therefore, how much is VO? VO equal to 0. So VO is 0. So when input is negative, VO is 0. And therefore, there's no circuit, no current, no voltage output. Yeah, so everything works perfect, fine. So that's why we call this a super diode, because when input is positive, you got 100% of input going to your load. When input is negative, nothing goes through. Now, of course, if you want to get a full wave, what you do? You do like a bridge rectifier. You would have like 4 of the circuit together, but we're not gonna get that far. But just give you an idea of a super diode. Okay, so next concept is we call a DC restorer. So by the name, you know what it means that if your input is AC, we're going to move everything up. We're going to shift everything up to get DC. So we get rid of the DC offset. I mean, we add a DC offset instead of adding remove the. So initially, like in this circuit, you have input coming in, -6 to +4 is VI, but at the output, you get a 0 to. Okay. Interesting. How can you do that? Well, it turned out to be very simple principle is when VI, that we can start. We can start from here. So when VI is positive, do you have current? No current. Okay. So no current. So this is okay to start with. But when VI is less than 0, what happens? You have current flowing, right? Okay. So in this case, assume that assume delta VD is, assume VD is 0. Now, of course, you don't have to assume it's 0, but certainly this simplifies our analysis. So assume VD 0, how much would you get for VC? So if we assume VD 0, current flowing through the diode, and then your VO will be 0, and your VC is a loop, right? It's one simple loop. So your VC will be minus VI. Correct? It goes this way, and all the VI is dropped on that capacitor. So it's like negative VI. And then initially VI is negative, so which means it's going to be 6 volts. It's going to be 6 volts, right? Because VI is negative 6, now VC is 6 volts. So the next step, when VI is positive, see what happens? Now VI turns back to positive. VI turns back to positive. Do you have current? No current, right? So no current, but let me draw the equivalent circuit for you. So we have this is positive 4 volts, and you have here to here 6 volts. So what is VO? You see, positive negative 6 volts, positive negative 4 volts, and you add it together, 10 volts. 10 volts. So it's very simple. Is that you would add a DC offset to the input, you get from 0 to 10 volts. Okay. Now, if you consider the voltage drop on the diode, it will be like 0.7 to 9.3 volts. Okay. So that's what you get. So this is called a DC restore. Now, of course, the caveat is that if you have a load connected at the diode, it's going to change the whole picture. So normally this circuit is only good for like digital circuits where you don't draw any current from the circuit. It basically gives you a voltage level. Okay, now it's negative. Now I move everything up. I got a voltage level. If you draw any current from it, and the whole thing is messed up. It doesn't work. Okay. Similarly, so this is a circuit similar to the previous circuit, but they call it bootstrapping. So bootstrapping is try to move the AC to DC. So instead, like AC, VI input is the AC signal on the right hand, on the left hand, is from negative VP plus VP. But then you have output VO on the right hand, which is VCC plus like diode, and you have a capacitor. So this circuit is very similar to what we talked before. So when VI is positive, so we start with VI is negative. So when VI is negative, you have this way. So when VI is positive, so when VI is negative, you have voltage. So therefore, you're going to charge this VC. You're going to charge this VC to a certain value. And you can write the loop equations. So this VC is going to be VCC plus or minus VI. So plus peak. So VIP. So yeah, so just write it. Plus it's a peak. When it's negative, but it's a peak value. So right. VP. When it's going positive, you see there's no current. So therefore, this VO will be VP plus VCC and this ideally, okay. So VCC plus VP. And this one is VP plus VP minus VCC. Okay, with VP minus VCC plus, no, actually the voltage will be from here to here. So it's going to be, so VO is going to be, so plus minus, so VCC plus VP, then plus VP. So it's called VCC plus 2VP. So the output goes to VCC plus 2VP because we are measuring here. So it doesn't matter here because there's no current here. So measure this voltage plus this voltage gives you output. But this voltage was initially to be VCC plus VP. So that's how we got the output. If you plot the waveform, it looks like this. So output is going to be moved up from negative all the way to VCC. So if VCC is zero, you would just get this. So if VCC is zero, you will get, oops. So if VCC is zero, you get this waveform. Actually, what you're doing is you're shifting the AC up to a certain value. Oh, no, sorry. No, this is wrong. I was drawing the rectifier. So this is a waveform that you get if VCC0. Okay, so finally, we have what we call a voltage doubler. So by the name, you know that what it does is that it doubles the input voltage. So input is 1, the output will be 2. Input is 3, the output will be 6. And it doubles the voltage. We got 2 diodes and 2 capacitors that's working. So what we can do, for analysis, like we can start with if Vi is positive. So Vi is positive, current goes through this Vc, so Vc1. So we can charge Vp, we can charge Vc1. So you see, if Vi is positive, you have current flowing because D1 is conducting, right? When D1 conducting, you charge capacitor, C1 to Vp. Okay. So Vc1 is equal to Vp. And then if Vi is less than 0, you have current flowing this way. You have current flowing this way. Now you count VO is hard to reach there. But when you have Vi is less than 0, your current flowing from bottom through C2 and all the way to Vp. So now because maybe, you know what? I draw a equivalent circuit to make it easier to understand. I'm going to do this. I'm going to draw a equivalent circuit like here. So Vi is negative, right? So Vi is negative means Vp is bottom is positive, up is negative. And you have Vc also bottom positive, or left positive, right negative. So now if we write together VO is basically Vp, it's like one Vp plus another Vp. So basically about 2 Vps. So negative 2 Vps. Right? So plus, minus. Yeah. So if we write this equation here, so which means VO will be negative 2 Vp, now 2 Vp, negative 2 Vp. So that is why we have the circuit over here is that you basically drop here minus 2 Vp. So we shift everything down to 2 Vp instead of that sinusoid waveform. So it's like your output is doubling the input peak. So when input is certain peak, the output is doubling that peak. Okay. So that's the voltage doubler. Voltage doubler, you can also do a DC voltage doubler, but you don't have Vi. You can be like a different waveform and so on. I probably don't have time to go through all this. Initially, I wanted to do some simple examples, but when you guys do these examples, just pay attention to what you're required to do. If it tells you it's an ideal diode, no voltage drop. If it tells you a piecewise linear model, 0.7 volt drop. If it tells you it's 0.7 at 1 milliamps, remember you have to bring back that exponential equation to calculate the current or voltage drop. So that's the only thing you'll be careful about. So given that, I think we're going to conclude today's lecture. I'll see you guys on Thursday. Good luck with the exam.